Well, welcome back today for our discussion about trial and error searching. This is a little bit different than the earlier stuff we've done so far because we're almost doing science. What we've been doing is sort of basic computing science, basic numbers, representations, but now we'll get on to something we actually have the computer do something which is not at all obvious. And it's called trial and error searching. And that's a very interesting term. It reminds me all the time of a spaniel trying to find a ball that you throw in the yard. And how does a spaniel find a ball? Well, you know, they first go to the place where they think the ball is, and it's never there. So they sniff around, and then they run around in a circle. And they look for the ball with their nose to the ground. If they don't find it, they just make a bigger circle. So that each circle is a new trial, and each time, if they don't find it, it's an error. So they go ahead, make a different trial. We'll do the same thing now, but we'll do it with a computer. And what we try to do is the very simplest problem one can think of. We have it here on slide number 2, and it's root finding by trial and error. And when we say root, it's sort of a mathematical term. It means let us find when a certain standard form of an equation, f of x, that's equation 1, is equal to 0. So when we say a root of an equation, we mean let's find when an equation, f of x, is equal to 0. Let's find the roots. Very basic. It represents the solution of many possible problems in science, engineering, anything. Now some of you may be thinking, whoops, what if I don't have an equation in the form f of x equals 0, but say it's like equation 2 up here, where it's g of x is equal to h of x, where g and h are just names, just for some arbitrary functions. Well, then okay, you just say the new function f of x is just the difference, g of x minus h of x. And that's what we want to be equal to 0. And when that difference is 0, then we know g and h are equal. Okay, so the way you do this on a computer, and what's interesting, is that we search for the solutions by guessing. And they're not just dumb guesses. It's not just saying it's 3, no, it's 5, it's 6. No, it's an intelligent guess. In fact, the first guess has to be semi-intelligent for many of these kind of methods, or you're led nowhere. You could be led astray further off. Okay, so we start off with a guess, but since we don't want non-scientists to think we're just guessing around, it doesn't sound good, we call it a trial. That's like a spaniel going around in the first circle. And then we try the trial, and we see how bad an answer we get compared to some criteria we set up. We say, aha, I know how to improve the guess. So this is then an intelligent procedure. Okay? And how do we end? Well, we end either when we found the place where the function is equal to 0, but that never happens. That's a strong statement. Why does it never happen? Well, if it's a scientific problem and we're solving something in floating point numbers, the 0 you get, even if it's 0 floating point, is never a mathematical 0, unless it's all integers, and it won't be for this. So really you're finding when it equals to 0 within some level of precision, some tolerance. So here we'll say, okay, we'll find when it's equal to 0, or at least when it's smaller than some number epsilon, which we take to be small. We take the absolute value of f as smaller than that. The other choice, which you should always build in, is to say, we'll keep up this routine, we'll keep going around in circles, making guesses, until we get an answer small enough to be acceptable, or until we're just exhausted, until we've decided, I've made enough guesses, 100, 1,000, that this is just not a good procedure. And that always should be something you think of when you do computations. Build in the worst case scenario. Quit if you're doing something wrong, if the code's wrong. It reminds me of a quote in a biography I once read of JFK, the president, and his father used to get all the boys, the whole family together at the table at dinner and ask them what they did every day, and people would have to recite. Then he would tell them, try harder, try again. Remember, if at first you don't succeed, try, and then quit. And that's what we do here. Okay. So, what's interesting? Two interesting things here. First of all, we call it trial and error, and here's an algorithm we have to develop. We can't tell you ahead of time how many steps it'll take. Okay? So it's not completely deterministic. It may work, it may not work. That's fun. That's interesting. That means the computer's showing some kind of intelligence, and the computer's adapting. It's an artificial intelligence. The computer's making decisions based on the outcomes that come. So this is an example of what we call artificial intelligence. So let's start off with the first basic, simplest kind of search algorithm, and it's called the bisection algorithm. So it tries to do the obvious thing, tries to find when a function f of x is equal to 0. The good news here is, in many cases, you can evaluate the function, say, at a very large value of x and get it to be positive or negative. You can evaluate at another much smaller value of x and have the function occur with a different sign. So if you know there's a sign change in some region, then you're set. You can't lose. You have to be able to find a 0, because a function can't change sign without going through 0. So for example, if we look at the diagram here, we see here, don't worry about all the spaghetti and all the notation, we'll talk about that. But here we have a curve in black, it's a parabola, and down here on the left side we see, aha, it goes through 0 someplace. But you don't know ahead of time where it goes through 0, although you're allowed to draw graphs, and it's a good idea to do that. But if it goes through 0, we'll say, aha, the 0 is the middle, plus is where the function's positive, minus is where the function's negative. That's all the bisection algorithm requires. As long as you know the function changes sign, then we can go ahead and find that where it crosses 0. It's not a smart method, but it always works. It's like a spaniel. Okay. So we start off mathematically by saying f of x minus is less than 0. So the minus signs just mean that's where the function's negative. Okay? And there must be some place, f of x plus, where it's greater than 0. The algorithm, in other words, the recipe we use, is very simple. In sort of pseudocode, we say, first we just assign a guess, a new value of x for where the 0 crossing should be, and we say it's just the bisection of x1 plus x2. Okay, it's just the sum of the two divided by 2, just the average. So we just bisect the difference. That's it. That's our new guess. And then we make one simple logical test. If the product of f of x, that's f at the new guess, times f at the old guess, where the function was positive, if that's greater than 0, then we know the function has not. I repeat, if the product of the two is greater than 0, the function does not change sign. If it hasn't changed sign, we may as well say, why don't we choose the new value for where the function's positive to be the guess we just made. So in a sense, all it does is move a little closer in. If that's not true, else, in other words, if the function does change sign, aha, then our new guess is a place where the function is negative, and then we may as well choose that as x minus. So recall, x plus is a place where the function is positive, x minus is where it's negative. So all this does is it makes a guess, see it if the function changes sign. If it does, that's the new negative x minus. If it doesn't change sign, then it just moves in a little bit. We narrow the region down by a factor of 2. That's why it's bisect. Each time, till we get close. Mathematically, we never get the answer, but it can get very close. Okay, so here, in the diagram on the left, in beautiful gray, white, and black, we see the procedure in action. So let's see. Look at this closely. I hate small print. I wish the authors wouldn't do that all the time. But anyway, here we have x minus. So that's our first guess where the function is negative, less than 0. Here's x sub plus 1. That's our first positive guess. So there's a line connecting the two, and geometrically what the bisection algorithm does is it bisects, chooses the guess for where the 0 should be at x2, this case right there in the middle, and then it goes down and says, aha, evaluate the function, and it's negative. The function's negative, I'll call that my new negative guess value. Okay, so that limits the range. So this is x minus 2, that's my new guess for the negative limit. X plus 1 and x sub plus 2 are the same, okay? Because the left-hand side, the positive side hasn't changed, so my new guess will be someplace in the middle, right here, x3. When we go down, we see, okay, x3, I evaluate the function, it's smaller, it's still negative, so x3 becomes now x minus 3, same as x minus 4, it becomes my new right-hand limit for the interval, and I do it again. So my interval is now the small interval here from x minus 3 to x plus 3. The guess is in the middle, and boom, x4. I come down, I see the function's positive, so now I know I've gone a little too far. I call that my new guess, and I just keep narrowing the interval by a factor of 2 in each step until I get close enough. So it's slow. It can't fail, but it's a good way to start. It's a good way to get close if all else fails. Okay. So what's a better way? A better way would be the Newton-Rapson algorithm. So we talk about that on slide 4. Take a look. So the idea here is also easy to understand geometrically. This is always quicker. It's more robust than bisection. I take that back. It's always quicker than the bisection algorithm, but it's less robust. And we'll see what that means. The bisection always works. This, when it works, is very, very fast. It's quadratically fast. Okay. But it can easily fail unless you're careful. And there's ways of fixing it up. So the whole idea here is, and let's talk about it first geometrically, because it's a little bit easier. If this is our same function we've looked at before, we say, let's take a tangent, which we can evaluate numerically very well. We start off with a guess 1. We draw a tangent to the curve, the function we're trying to fit, and we look where the tangent goes through 0, right down here. Aha. So if the tangent goes through the 0 there, we take that as our new guess, brings us up to point 2. And then we evaluate the function at point 2, and we evaluate a tangent of it, and then we make point 3 here our new guess. It's so close you really can't tell the difference. So here in 3 steps, we've gotten as close as we can be. Okay? So how do we do that? Analytically, we see here in equation 3, the approximation is to say some function f of x, we know ahead of time, will approximate it by a straight line. We'll say it's a linear function, at least when we get close to the 0 point. Because every curve looks like a line if you magnify it close enough. So for a small enough region, presumably this region right about where the 0 is, we want to have the equation of a straight line. But if we have the equation of a straight line, we can solve for where the straight line goes through 0. Very simple. We just solve for x when f of x is 0. So x is minus b over a. Okay? So if we approximate a function as a linear way, we determine a and b, in other words, just numerically, then we can guess the approximation. Okay? That's the method. What can go wrong? Well, what we see here is that a few things can go wrong. If the function has a local minima or maxima, such as point 2 here, that can give us a real problem, because if we start at point 1, we go down to the bottom here, we get to point 2, and the function is flat. So when we find a tangent to the function at a flat point, either a maxima here or a minima, it sends us out to infinity. Well, you don't want to be at infinity if you're trying to find a 0. So one approach, which you can try out, one approach is to say, let's not take a full step. You only take part of a step, or you keep making the step smaller and smaller until you only get closer to the 0. You never let yourself get far away. So that's how you avoid that. The other approach, which is not so easy to solve, is to say, what if the function has this kind of funny shape? We start off at point 1, we then go down to point 2, we then find a tangent at point 2 takes us to point 3, we go to point 3, which takes us back to point 1, so we just get in an infinite loop. So it doesn't get further away from the 0, it doesn't get any closer, it just stays going around. And that's something you can have to build into your code to watch for. Okay, so now let's talk about how we look at the analytic way of doing this Newton-Rapson. So now let's look at slide 5. Slide 5 has a bunch of equations. They're not trivial to understand by just staring at them, but they're actually quite simple, and you can derive this on your own. Probably you'll see be asked a derivation of it on the exam. It is very simple. It's a very powerful technique. So how do we do now mathematically just what we spoke about? How do we fit a tangent to a function and then determine when the tangent goes through 0 then use that to give us a better guess. Okay, so go ahead. So right here at the top, we want to solve again, f of x is equal to 0. That's fine. We now have to be careful. We'll define x sub 0 as the initial guess, or the 0 you can think of as the old guess. That's the guess, and it should be a good guess, where the function is 0. Let's hope it's pretty close. Sometimes you may want to use the bisection algorithm to get close, then you switch to this. So it's a good guess. Now we need to compute the unknown correction. So delta x is what we're solving for. We know x0, we're free to make any guess we want. So the new guess will be the old guess, x0, plus the correction, delta x. So we call that x1. So the whole procedure, if you want, goes from x0 to x1, x1 to x2, to we quit, same way as before. Okay. The difference now is we say, well, we know if we're here in equation 6, we know that if we're near the solution of our problem, then we can expand the function f, x equal to x0 plus a small correction delta x. So if delta x is small, we can use a Taylor expansion. And to be simple-minded, which is always the best way to start, we just keep the first two terms in the Taylor expansion. So equation 6 has f of x0, which is just a number, the constant, 3, 6, 12.8. The derivative of the function f evaluated at x0, which we know. We don't know, it's easy to compute on, the computer knows it. Okay? And then delta x, which is the unknown. So we have an equation here, we know everything in the equation except the correction, so we just solve for that because we know the function, or this is the real assumption one makes, we assume that the function as expressed in terms of the Taylor expansion is 0. Okay? So if the function is 0, then we can solve for the correction. And we get that the correction, f of x, at delta x, is equal to, with a minus sign in front, f of x divided by the derivative, divided by the tangent. And we see here mathematically, oh, well, if the derivative ever goes to 0, we shot out to infinity, that's the local minima and maxima. Now if that happens, then you just make a more intelligent guess. Change the guess. Okay? Okay, so that's everything we need to know. Oh, what? Oh, okay. How do we do the derivative? Well, if you know the function, we haven't yet really spoken about derivatives. So either you read the book, right up there is the book, you should go read it. Read the book, and if that doesn't work, then evaluate the derivative numerically, and here's an easy, simple way to do it, which is never the wrong answer. It's never the right answer, but it's never too wrong. Just do it numerically by taking a difference. Evaluate the function at x plus delta x, which is what you have to do anyway, then subtract the value you had before, divide by delta x. That's a good approximation to the derivative, and as you get closer and closer to the 0, it gets better and better. So, now it's probably a good time for you to try out these two approaches in the lab. So we've showed a very simple approach, the bisection algorithm, then a more sophisticated approach. You should look at both. So now let's go on to the lab. So now it's time for us to try some trial and error exercises in the laboratory. So we have two for you to do, and they're sort of the obvious ones. First exercise is we want you to find quantum bound states. And I know you're probably thinking, what is he talking about? Quantum bound states? I don't know how to do that stuff. Okay. Well, the hard part we've done for you anyway. Here's what we have. We have a very simple problem. We have a quantum well, which is just a potential, a box. And we have a particle, think of it as an electron as you want, which is bound. It's just bouncing around in this box some way. And the box has to be small. It has to be appropriate size for an electron to be bound, which is the size of an atom. And you're asked, calculate the energy. What energy can a particle have inside of a box? And one of the things you learn in quantum mechanics is energies tend to be quantized. They tend to have definite values and not continuous, just discrete values. So you're asked here, what values could it have? So the hard part, which we don't make you do, is to say, okay, the answer is the energies are the solution of this equation. This rather simple-looking equation has a lot of quantum mechanics built in, or this rather complicated-looking equation has some transcendental functions built in which it's hard to solve for. So the energy E is a solution of this equation. Square root of 10 minus E times the tangent, the trigonometric function, tangent of the square root of 10 minus e is equal to the square root of 10 minus e. So this is a transcendental equation. It should have a solution, but it has no analytic solution that we can write down. That means, in some maybe philosophical sense, you could say it doesn't really have a solution because we can't write it down. Maybe that's true. Maybe we're just not smart enough to write it down. But we can solve it numerically, and you can prove that it has an equation, it has a solution, so it's a nice equation. Okay? So, that's your exercise. Solve this equation. Find the root of the equation. Okay? And remember, the roots have to have f equals 0, but that's easy enough to do. Relax. We're starting you off, it's the beginning of the course, and if you look on the disk, you'll find a program, bisection.java, if you're programming in Java. If not, there's a C or a Fortran version. If not, look for it on the CD someplace. And that program should solve this equation for you to get you going. So either write your own, use this as a guide, or modify it. And what it does is it uses this bisection algorithm to find an equation, find a solution. But remember, one of Landau's rules said traumatic experiences make the best learning experiences. Well, if the plan works out as we planned it, the program should fail. Why is that? Well, that's because this equation, this function, has some infinities in it. It is not a trivial one to solve. Tangent, if you recall, of 0 is 0. Tangent is sine over cosine, and at 90 degrees, or pi over 2, the tangent is equal to infinity. So you need to plot the results up as a function of energy, make a plot of the left-hand side of the equation versus the right, or take the square root of e over, so you get a plot of what the function looks like as a function of e. And I'm not giving it to you here because I want you to look at it yourself and do something for your homework, otherwise we're giving the whole course away. So plot this up and you'll see there's a singularity. Singularity is just a fancy term meaning something singular happens. Something singular means very big. In this case, the function is equal to infinity. And that messes up these search routines. They get kept away. The infinity confuses them. Doesn't confuse the numerics as bad as it does some of the other routines, some of the analytic approaches. So, in point C here, we say, okay, let's be clever. In this case, if the singularity of the tangent is very close to where the solution of the equation is, which it is, it's hard to find the solution. But you can transform this equation into a mathematically equivalent form because tangent is just 1 over cotangent. So if you substitute tangent 1 over cotangent multiplied through, we get this other equation. Okay? That's a cotangent equation, and that has also singularities, but they're not close to the 0. So this is being smart. It's another kind of intelligent guessing. We have to guess, but we have to manipulate the equation to put it into a form which works, which we can find a solution. So we may try this. It should fail, or it may not be a good answer. If you look at a plot, you can get a good answer. But now, how do you look at a plot? Well, you could do it by hand with a calculator, which is a good idea. Many of the students, particularly if you're taking some of the introductory classes, you know how to use Maple or Mathematica. You can use those to make your plot. Go ahead and do it. I'd like you to. I challenge you to. Why? Well, it turns out not only do computer programs, but Maple and Mathematica, which are just computer programs too, they often have trouble plotting this function up accurately because of the singularity, or finding solutions of this accurately for the same reason. So likewise, they may be better with equation 2 than equation 1 for the plotting. Try both, see what answers they give you. Okay. So that's the first exercise. A very simple equation. It's important in quantum mechanics, even if the potential is much more complicated. You end up still having to find a root, find an eigenenergy, they're called, by trial and error. Important problem. This has to be the simplest way to solve it, the only way to solve it, but nevertheless, you have to be careful. Okay? So as I said, this is like science. There's no obvious answer. It's not pure mathematics whether there's a solution or not. You have to look and see. This is doing an experiment. Okay? Exercise 2 says, do the same thing. Again, but use the Newton-Rapson method. So you know where the solution is now from your graphs. You have a rough answer. See how much quicker Newton-Rapson is. See if it doesn't fail. Solve the same equation. Okay, equation here in line A. And now compare your results to the bisection algorithm. And now try some physics. When you get the method to work, here's our well again. And the energy E is what you get out. And now it seems obvious that this is where the particle's energy must be. If you pull the bottom of the well down to make the well deeper, you can get, the energy should get deeper. You may even get more than one solution. You may get several possible solutions. See if that's true. Okay? So the 10, the number 10 that appears in this equation is not an actual constant of nature. It's proportional to the depth of the potential. So if you make the number 10 another number which is larger than 10, can't make the number 10 bigger because it's 10, but make it another number which is larger than 10, say 20 or 30, see if the energy moves down. See, in fact, if there may be enough more solutions. And I guarantee you, it's sort of optional. If you make 10 much, much larger, you get more and more possible solutions. Plot up the function for different values of energy. They'll have many zeros. Okay? So that's further exploration. So now I think it's time for you to go into the lab and see if all these words can be turned into computer programs and numbers and get something to work. Okay? So enjoy your exploration. Bye-bye.